Swayam Prabha. Digital India. Educated India.
Okay, so let us continue our discussion of coherent state path integrals. So, if you remember what is coherent state path integrals, basically it is about wanting to study quantum mechanical systems using Lagrangians, but rather than think of the Lagrangian as involving the usual generalized coordinates like the position and the velocity, that is q and q dot. That is how you normally think of your classical Lagrangian. Basically quantum mechanics can be re-derived, or basically it can be extracted from a classical Lagrangian by saying that you see, not all paths are so in other words, usually what happens is that if somebody tells you the classical Lagrangian, that is L of q comma q dot, then you know that if there is one path which obeys the Euler-Lagrange equations. So, that is precisely the classical path, but a quantum particle is not going to always select the classical path. So, what you do to study quantum mechanics is using Lagrangians is you say that you see, all paths are allowed, but each path comes with some weight, and that weight is basically proportional to e raised to I by h bar times the action. The action is it's basically the time integral of the Lagrangian. Lagrangian integrated over time from some initial to final time. So, basically the weight itself is a complex number of unit modulus. So that is the funny thing about the path integral approach to quantum mechanics. Basically it does not tell us that, in fact superficially it seems like all paths are equally probable, because you see so basically what path integral approach says is that if you want to find the average of any expectation value of anything, what you have to do is basically rewrite this in terms of the action and divide by the so you integrate over all paths and then you divide by the appropriate normalization. So, this presumably depends on the path. So, this will depend on x dot, whatever it is, it can depend on x dot, but bottom line is you are integrating over all paths, all x's. So if you have some x1 t1 xi ti is your initial and xf tf as your final, then there will be a whole bunch of possible paths. So, what this says is that all of them are allowed in quantum mechanics. See, unlike in classical mechanics, only one path is allowed, all other paths are strictly forbidden, only one path is allowed. But in quantum mechanics all paths are allowed, but each comes with a weight. And the funny thing about this weight is it is a complex number of unit modulus. So, that means that if you just look at the absolute value of this weight, it is 1. So, implying therefore that it seems like the probability of the particle choosing any path is pretty much the same, which seems rather counterintuitive and paradoxical, because we expect classical paths to be slightly more favored even in a quantum system. But the reason why that is I mean the reason why this approach is not wrong is because you see that your intuition that the classical path has to be slightly favored is recovered by a realization that the Planck's constant is the one that is very small. So, when it is very small, the this is a phase term, it is going to oscillate rapidly, and most of the paths kind of they cancel themselves out, because as you move along the path, the phase oscillates rapidly because of the smallness of the Planck's constant. So, the only paths that are likely to contribute substantially are those which minimize the action. So, you see, because h is already minimized and it is in the denominator, and you had better minimize the numerator also, otherwise the ratio is going to be infinite, and if it is infinite, e raised to I times infinity kind of rapidly fluctuates between plus and minus 1 and averages out to 0. So, if you want to prevent that from happening, you should ensure that the Planck's constant, which is very small, will also imply that the action is as minimum as possible. So, to try to keep pace with the catch up with the smallness of Planck's constant. So, bottom line is that that is how you recover classical physics from this path integral approach to quantum mechanics. So, now this coherent state path integral is not about studying this path integral using this approach, where this approach is about integrating over paths, and your action depends on the position and generalized position and the generalized velocity. But I want to study, I want to write down a Lagrangian not in terms of the usual generalized position, generalized velocities, but I want to write it in terms of the classical analog of creation and annihilation operators, because see, generalized position, generalized velocities are classical versions, I mean they are classical variables. But however, you see in quantum mechanics, when you rewrite your Hamiltonian in terms of creation and annihilation operators, you get A and A dagger, and these are complex. So, if you want to now study the same system, which is now expressed in terms of these creation and annihilation operators, which are complex operators, then you are forced to invoke the notion of a complex eigenvalue of these operators, which you can then use to construct a Lagrangian in terms of the eigenvalues of A and A dagger. So, which is precisely what we have done here. This is what that is. This is basically the e raised to I by h bar. Again, I keep forgetting the h bar that is there. So, it is e raised to I by h bar integral of the action, and this is my action for the harmonic oscillator in terms of the coherent state, in terms of the eigenvalues of the creation and annihilation operators. So, now as usual, you see this is if I wanted to calculate the expectation value of some some Green's function, but let us only focus on this, okay, because I have to integrate over endpoints and all that. So, I have done, but let us focus only on this. So, now if I want to evaluate a path integral, how did we do it in the case of harmonic oscillator when we were studying it in the x dot language, that means in terms of the original position and generalized velocity language. So, the way we did that is we looked at the classical solution of the extremum, the path which extremizes the action, so that we can then go ahead and expand our path around that extremum. And so, in order to find the extremum, we look at the variation of the action and set it equal to 0, and following very standard methods we get these equations. So, this is the classical path that comes out. Now, you see we have to also ensure that so if the starting path is, I mean the z value when it starts off at t equal to ti is z0, then z when it at the end point t equal to tf, we postulate that the z value is zn. So that therefore the Zn and Z0 are related in this way. They are related to Tf and Ti. Again, I keep listen. I mean, I have put h bar equals 1. Otherwise, it's h bar omega into. Oh, sorry. Now it's still omega. Omega is frequency. T is time. That's fine. Okay. Here it's fine, but there I should have introduced it. Now, but nevertheless, bottom line is. So now what you do is you rewrite your path as the classical path plus deviation from the classical path. So this z tilde is basically deviation from the classical path, and because all paths start and end at the same point, the deviations should become 0 at the starting and ending points. Okay. So now if you substitute that, you will see that all cross terms drop out, and you will get a classical answer multiplied by this quantum fluctuation. Okay. So the point is that you see the advantage of, you might think, why do we always split it up this way? Why do we split up the path in terms of a classical path plus a quantum fluctuation? See, the reason why we do that is because the quantum fluctuation now obeys periodicity. Because the original path there is no periodicity. At t equal to Ti it's Z0, at t equal to Tf it is some unrelated Zn. So there is no connection between Z0 and Zn. But however, by construction Z tilde is 0 at t equals Ti, it is also 0 at t equal to Tf. So that implies that this periodic function of its argument where the period is basically Tf minus Ti. So that is what I have done here. So I have constructed a Taylor series where the function vanishes at both Ti and Tf, and it's periodic with respect to time with period Tf minus Ti. So this is the most general way of doing that. So now you can go ahead and evaluate this particular integral. Okay. So if you evaluate this particular integral, look, I have used conventional methods now to evaluate this path integral. So I have just pointed out that you could do it this way. Yeah. So rather I have evaluated the rest of it. I have evaluated this. So you see, when I do that, I end up with this. So this is still there. This is the integration over quantum fluctuations. The rest of it has been evaluated. Yeah, because finally we are going to be able to compare. So this is the coherent state path integral. This is the coherent state path integral version of the Green's function. So it's basically the coherent state path integral version of the Green's function. But there is also the Hamiltonian approach to this calculating the Green's function, if you recall. So this is the traditional Heisenberg picture. Well, in this case it's it's the Heisenberg picture. Well, you can think of it as it's actually Schrodinger picture, because see the states, this is a state which evolves with time. So it has evolved from Ti to Tf. So you can go ahead and evaluate that. Okay, so if you evaluate that, you will end up with this result. I mean, it's a little bit of a tedious algebra. Okay, so you will end up with this result. Okay, so now this is the result that you have obtained, and this is equal to whatever we got way back. So basically, what this approach tells you is, it tells you how to evaluate. So remember that this was some constant. So this was some constant which was it was one of those GTF minus Ti types. Yeah, so that's what it was. So bottom line is that it was something like that. So that's what it was, GTF minus Ti, and the rest of it gets evaluated. So it's a lot of tedious algebra, and you have to go through it. So most of the interesting dependencies are already contained here. This is that G of Tf minus Ti. Okay, so bottom line is that with some effort, you can convince yourself that the coherent state path integral approach for the harmonic oscillator gives you the same Green's function as you would get if you did the conventional path integral for the quantum harmonic oscillator using position, coordinates and generalized velocities and so on. So, yeah, so that is important, and it's important for you to understand that, because you'll see that in the end I am going to be able to generalize these two fields, because after all the systems that we are studying are quantum fields. So, till now I have only introduced point particles. So, that is one mass tied to one spring, and I am studying that quantum mechanically using a whole bunch of approaches, whether it's starting from the original Schrodinger's approach of wave functions, Hermite polynomials, then writing in terms of creation annihilation, and studying in terms of those ladder operators and so on and so forth, or studying the quantum harmonic oscillator Green's function using the conventional path integral, which involves position, generalized velocity, in this case xt and x dot t. So, and lastly I studied the classical counterpart of a dagger a plus half into h bar omega. So, that is basically the coherent state path integral approach. So, you construct the adjoint of the Hamiltonian with Lagrangian, and the Lagrangian will be basically classical, because it will be classical because z and z dash are complex numbers which are commuting with each other, and you integrate over all possible such complex number paths, and then you get the same Green's function as you would if you had done conventional things. So, now the question is, how do you so this was all harmonic oscillator a dagger a plus half. So, that means the commutator of a and a dagger is 1, but then the commutator is 1 means basically you are studying bosons. But in nature you know that there are other types of particles called fermions. So, you should be able to study fermions also, because after all electrons are fermions, all these quarks, leptons, these are all fermions, and the bosons are all the force carriers like photons, gluons, W and Z bosons, and whatever. So, those are all bosons. So, typically bosons are force carriers, and material particles are fermions, and since both exist in nature, we should be able to study both quantum mechanically, and both are thought of as excitations of some field. So, just like quarks and leptons are excitations of a suitable matter field, a quark field or a lepton field. So, similarly photons are excitations of the electromagnetic field, and the WZ bosons are excitations of the electroweak field. Basically Weinberg, Salam and Glashow unified the weak force with the electromagnetic force. So, that is called the electroweak theory. So, the fields there correspond to basically excitation of the electroweak field. So, that could be either photons or the W boson or Z bosons. So, then you have strong forces which is responsible for holding the nucleus together. So, the strong nuclear force, the material particles are quarks, but the force carriers are gluons. So, basically you need a theory which describes not only gluons, like a dagger a would correspond to, because gluons are bosonic particles, so they will correspond to a dagger a type of thing, but fermions will be also important, because you see the material particles are fermions. So, we should be able to do we know how to do the conventional type of quantum mechanics using creation and annihilation operator for fermions. That is quite easy, because after all if you have a finite system, then if you have a suppose you have a state, you want to create a fermion, you can't create one more unless that fermion comes attached with some label like spin up or spin down. So, if it does not come attached with any label, then you can create either one fermion in that level or no fermions. Yeah, so the question is the following. So, how do you study fermions using path integrals? That's an important question, because you see, in order to study anything using path integrals, you should first construct a classical Lagrangian. So, even though you are studying quantum mechanics, you have to first construct a classical Lagrangian, and then you construct the classical action, but then you do not, that is where you stop. Then you do not go ahead and write down the Euler Lagrange equation. Rather, what you do is you insert the classical action in the exponent of some weight. So, that means you construct a weight of the form e raised to I by h bar times the action, and that weight is what tells you how much weight a certain quantum mechanical path, basically how much weight a path has when a quantum particle traverses along that path. So, that weight is basically proportional to e raised to I by h bar s. So, therefore, in order to do path integral approach to quantum mechanics, it appears that you really need a classical Lagrangian. But the funny question now is, how can you construct the classical theory of a fermion, because that is what it seems to imply. Because you see, there is a classical theory of a mass tied to a spring. This is basically the classical harmonic oscillator, because the quantum particles or the excitations of mass tied to a spring manifest themselves as bosons, because A and A dagger they have the commutative property, that is, commutator of A and A dagger is 1. However, there are particles in nature that do not manifest themselves as bosons, they manifest themselves as fermions. So, now the question is, are there objects in nature that correspond to classical analogues of fermions? Because you know that there is a mass and there is a spring, and you tie them together. That is what a classical analog of a boson would look like. Meaning, in some sense, the boson comes out by quantizing a mass tied to a spring. So, the question you can naturally ask is, what classical system when quantized gives you fermions? Is it mass tied to a spring? No, it will give you bosons. Then what tied to what will, when quantized, give you a fermion? So, the answer to that is basically nothing, that there is no classical analog, at least that is the conventional answer. So, there is no classical analog of a fermion. So, that means there is nothing which when quantized gives you a fermion. The fermion is already quantum. Basically, there is so usually you are given the impression that quantum mechanics is kind of not possible unless you have a classical description to begin with. That is how you are taught quantum mechanics, and of course, with good reason, because most of the systems do have classical analogs. So, it makes perfect sense, like the electromagnetic field. It has a classical analog and with the classical Maxwell equations, and then when you quantize it, you get photons. So, the question is now, which classical set of equations which when quantized will give you something like an electron, which is a quantum particle. So, the answer is unfortunately nothing. There is no classical system which when quantized will give you an electron. An electron is already quantum and there is nothing classical about it, that there is no classical version of an electron. There is a classical version of a boson which is mass tied to a spring. There is no classical version of a fermion. So, we have to learn how to. So now we are stuck, because we need a classical Lagrangian to do path integrals, but then there is no classical system as such. So, we have to cook up something. So, that cooking up something will involve using some very strange mathematics. So, that strange mathematics tells us that the eigenvalues of the creation operator of say, if suppose C is your annihilation of a fermion. So, suppose you have a, so if you have a state you can either have one fermion or no fermion, because it doesn't come with any other label. So, if I take that state which does not contain any fermion and I try to annihilate it, I am going to get 0. Now, I can construct a state with one fermion by acting the creation operator on that state with no fermions. Then if I try to annihilate that, I get a state with no fermions. But more importantly, if I try to create one more fermion in a state that already has a fermion, I get 0 immediately because of Pauli principle. So, you see, now what we want is this Pauli principle is this anti-commutation rule. So, the point is, what we want to do is we want to create, so in other words, we want to construct the eigenstates of the fermionic annihilation operator. So, because the eigenstates and eigenvalues of the bosonic annihilation operator are simply complex numbers, any complex number can be. So, basically you pick a complex number, you can construct a state labeled by that complex number, which will automatically be, by suitable construction, an eigenstate of the bosonic annihilation operator. But now if you ask the question, can I do that for a fermionic annihilation operator? Well, formally you can always write this, because you can say let eta be that eigenvalue which corresponds to the eigenvalue of the fermionic annihilation operator, and this is what it is. But now you see, keep in mind that C squared is 0. That is, if you try to annihilate twice, you will get 0. So, now suppose you act this supposed eigenstate equation, eigenvalue equation by another annihilation. What will you get? This will become C squared, which is 0, but then this will give me C times eta, which will give me eta squared, because C times eta is another eta times the state eta. So, the eigenvalue times the state. So, there is already the eigenvalue there. So, if I multiply the two eigenvalues, I get eta squared, but this is 0, C is 0. So, eta squared should also be 0, because the state itself is not 0. So, what that means is these eigenvalues are non-zero, because obviously they are non-zero, they are supposed to label some non-trivial eigenvalue, but their square is 0. So, obviously they cannot be ordinary complex numbers, because there is no ordinary complex number which is not 0, but whose square is 0. But in mathematics there are objects that have these properties, and they are called Grassmann numbers. They are called Grassmann as the name of some mathematician. So, it is Grassmann variable or Grassmann numbers. So, Grassmann numbers are numbers which have this property that if eta 1 is a Grassmann number and eta 2 is another Grassmann number, eta 1 into eta 2 is minus eta 2 into eta 1, and eta 1 squared equals eta 2 squared equals 0. Okay. So, these are the properties of Grassmann numbers, and moreover you can show that any function of some Grassmann number at most will involve just so if you do a Taylor series, see, if you do a formal Taylor series, what is this? It is f0 plus eta f dash 0 plus eta squared f, but eta squared is 0, because eta is Grassmann number, but eta cubed is also 0, because eta cubed is eta squared into eta, but eta squared is 0. So, eta cubed is also 0. So, everything is 0 except eta to the power 0, which is 1, and eta to the power 1, which is eta, and all higher powers are 0. If all higher powers are 0, any function of the Grassmann variable is linear. So, that makes some enormous simplification there. So, basically what will happen is that you can now go ahead and construct coherent states with these types of properties. So, now you can show that basically the Grassmann variables have these funny properties like this, because usually you think that if you use your usual approach like x and p type of thing, that you see what is this is, so if you act p x p like this, so on the one hand it is the eigenvalue p into xp, but on the other hand this is basically minus I h bar d by dx. So that therefore you will get an equation. So if you solve you will get I EP xp by h bar as your overlap. So x overlap p is e raised to I p x by h bar. So similarly here also you will get the overlap between this and this is something like that. But then you see, because these are Grassmann numbers, if you Taylor series, only if 0th order and first order terms survive, all higher order terms are 0, because eta squared is 0 and eta dash squared is 0, etc., etc. So similarly the Dirac delta function has this funny property that because we expect Dirac delta to be x delta x is 0, because you see the Dirac delta, this whole thing is 0 if x is not 0, but if x is 0 it is still 0 because the coefficient is 0. So the entire generalized function is 0. So if you think of this x as now a Grassmann number, so now you can see that because any function can only be written like this, so it is therefore mandatory that the Dirac delta function is the Grassmann itself. So and if you integrate over Dirac delta you will get 1, so the integral of the Grassmann is 1. So it's basically something like a definite integral. So like that you can construct many such, and the integration is same as that's the most bizarre thing about Grassmann. So so the thing is that if you integrate the Grassmann variable, so this is some kind of a definite integral. So it's the same as differentiating because once you differentiate, this whole thing becomes a constant, because f theta is anyway linear in theta. So if you differentiate, it becomes a constant. So a definite integral of a function over the Grassmann variable is same as its derivative, which is something very hard to believe, but it's true. So now you can just go ahead and just like case of bosonic coherent state, you have this over completeness. Here also you will have similar over completeness, but keep in mind that this is very simple. This is same as 1 minus theta dash theta. So it's not really, I mean, it's overkill to write it like that. So same procedure, we follow exactly the same procedure, and when you do, you will end up with something very similar. But except that now you have to evaluate the path integral, and even that is also very similar. Okay. So but when you evaluate it, you will get something much simpler than what you will get in the case of bosons, because there you can have as many bosons as you want in a state, but fermions you can have either 0 or 1, and you will get a Green's function that's incredibly simple like this. So I'll allow you to look through these steps because I probably won't even ask you these questions in the assignments, because it is important if you want to specialize in particle physics. I think condensed matter people don't use Grassmann variables that much, but particle physics people use it quite a bit, at least the field theory crowd of particle physics. So it's kind of worthwhile knowing it to some extent. So now you can generalize this to field. So you see, if you have an electron field, you can say what it looks like. So the coherent state path integral of electrons in a solid, because now electrons being fermions, you have the fermionic coherent state path integral of a Fermi gas, in a solid. I mean, so you can imagine that could potentially be useful. So I am going to stop here as far as path integrals are concerned, especially coherent state path integrals. I may not have done full justice to the subject, especially the fermionic coherent state path integral, but it's there in the book, so you should look it up. So I am going to spend the next 2 lectures, which will conclude this course, discussing my own research. So I have developed certain non-local operators in quantum many-body theory, which I believe are extremely important, but they are very underdeveloped, in the sense that they show a lot of promise, but they are extremely technical and very hard to manipulate. But I believe that if you put in the effort and learn how to utilize them properly, they'll shed very deep light on various aspects of quantum many-body theory. So I want to discuss those objects, and they go by the name of non-local operators in quantum many-body theory. So that's the last topic of this NPTEL MOOCs course, and I'll probably spend maybe a maximum of 2 or maybe 3 lectures, very likely 2 lectures explaining that. So after that I am considering this course as more or less done. So I continue to encourage you to ask questions over email, over live sessions. Try to ask specific technical questions after reading the text and listening to the YouTube videos. Ask me specific technical questions. Don't ask me vague questions like I did not understand this subject. So ask me a specific question from the chapter and I'll answer it. Okay, thanks for going along for the ride with me. So I hope even though you may not realize it now, you will find this, especially if you decide to specialize in theoretical physics, you will definitely sooner or later find whatever I have explained quite useful, even though it may not be apparent to you right now. So yeah, so I'm going to conclude in the next 2 lectures. Thanks for listening.